Okay, so we're going to prove that for every natural number n, that 1 plus 2 plus 3 plus dot 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 plus n is equal to n times n plus 1 over 2. And we're going to prove this using the principle of mathematical induction technique. Okay, so we're going to state that. So prove by PMI, principle of mathematical induction. So the first part of the principle of mathematical induction is the base step. So this just sort of convinces us that the statement is true, at least for the first few terms of the sequence, right? So we're going to consider the statement revolving around 1. Okay, so that's basically saying the sum of the first term is equal to this formula if you were to plug in 1. Okay, so this is pretty easy. So 1, because that's the sum of the first term, right, is equal to 1 times 1 plus 1 all over 2. So we have 1 is equal to 1 times 2 over 2 is 1. So we can see that the sum of the first term is equal to the formula if you plug in 1. So that means the statement revolving around 1 is true. Right? Now, let's go ahead and consider S of 2, just to make sure that this is all good, right? So consider the statement revolving around 2. This means the sum of the first two terms, right, has to be equal to this formula if you were to plug in 2. So that's 2 times 2 plus 1 all over 2. Okay, so 1 plus 2 is 3. And 2 times 3 over 2 is 3 as well, because 2 times 3 is 6. 6 divided by 2 is 3. So we can see that the sum of the first two terms is equal to this formula if we plug in 2, right? So this tells me that S of 2 is true as well. Now, the way we do PMI is after we convince ourselves in the base step that it looks like it's going to be true for all natural numbers, right? If we just continue this forever and ever. Instead of doing that, we look at the inductive step. And what the inductive step tells us is we're going to suppose the statement up to k is true. Okay, so we're going to suppose that the statement up to k is true. So this, of course, for some k contained in the natural numbers, right? So this basically says that the sum up to some k, right, is equal to the formula k times k plus 1 over 2. Now, the induction step or the inductive step tells us if we can assume that the statement we're looking at is true up to the kth natural number, and then from that assumption, we can prove that the statement works for the next natural number, which would be k plus 1. Then PMI tells us that we can do that indefinitely, right? We can do that over and over and over again. Thus, if we can show that from assuming that S of k is true, that S of k plus 1 is true, then we can show that this statement is true for any natural number that we choose. So that's how induction works. So let me go ahead and, so our goal, right, is to show that 1 plus 2 plus dot 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 plus k plus the next natural number, which would be k plus 1, is equal to the formula if we plug in k plus 1. So that sum up to k plus 1 is equal to k plus 1 times k plus 1 over 2. So we have this from our assumption. So now we're going to try to get S of k plus 1. So S of k plus 1 would start with 1 plus 2 plus dot 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 plus k plus k plus 1, right? So we assumed that 1 plus 2 plus dot 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 plus k is equal to k times k plus 1 over 2. So this is equal to k times k plus 1 over 2. So that this piece is equal to this, and then we have that k plus 1. still. All right, now we have the left-hand side for our s of k plus 1. Now we just got to work on our right-hand side. So this is equal to, k times k plus 1 over 2. And to add these two guys, we need a common denominator. So we can just rewrite k plus 1 as 2 times k plus 1 over 2. And now that we have a common denominator, we can combine the numerators. So this is k times k plus 1 plus 2 times k plus 1 all over 2. And what we can do is, since both of these terms in the numerator have a common factor of k plus 1, I can factor out the k plus 1, and I'd be left with k plus 2. And remember, what I want to do is I want to show that 1 plus 2 plus dot 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 plus k plus 1 is equal to k plus 1 times k plus 1 plus 1 over 2. And that's literally what I have. I can rewrite this as k plus 1 times k plus 1 plus 1 all over 2. So I've shown that, thus we have that 1 plus 2 plus dot 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 plus k plus k plus 1, right? We have that this sum, the sum up to the k plus 1 natural number, is equal to k plus 1 times k plus 1 plus 1 all over 2. So we've shown that the sum up to the first k plus 1 natural numbers is equal to that formula if we plug in k plus 1, right? We have k plus 1 times k plus 1 plus 1 over 2. This means that s of k plus 1 is true, from assuming that the statement revolving around k is true. Okay? Therefore, by the principle of mathematical induction, right, we have that for every natural number, for every n contained in the natural number, the statement about n is true. AKA, we've shown that for every natural number, for every n contained in the natural number, we have that 1 plus 2 plus dot 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 plus n is equal to n times n plus 1 over 2. Right? We've shown this, and that is the proof.